Again, for this next section, we're going to go back and look at how do we have variables, or how do we multiply variables that are interacting with each other. In this case, we've got x times y. And when you're multiplying variables, you have to have the same variable in order to be able to multiply them. So the solution to this one would just be xy, because there's nothing that you can do to it. But in our second example here, we've got x squared times x. Since we have the same variable, we can go ahead and multiply, or since we've got the same bases being multiplied together, you know that you can just go ahead and add your exponents, so you get x cubed. Well, we have basically the same type of rules that apply to working with radicals. In order to be able to multiply radicals, at least for right now, you have to have the same indices. So if we look at this first example here, we've got the square root of 2 times the cubed root of 3. So we've got an assumed index of 2 and then a known index of 3 there. We can't multiply these together, so the solution would be the square root of 2 times the cubed root of 3. There's nothing we can do to put them together. But for the second one, we've got the square root of 2 times the square root of 3. So we know that we've got an assumed index of 2 and an assumed index of 2 there. The indices match, which means that we can multiply the radicands together. So 2 times 3 is 6, so you get the square root of 6. So again, if you get confused and forget how you can multiply or divide radicals, just remember your rules for multiplying variables. And if you think about how you multiply variables together, that's often going to lead you down the correct path of multiplying radicals together. So in problem number 3, we're going to take a look at how this works. We've got 2 times the square root of 7t times 3 times the square root of 14t squared. Now, one of the things that I want you to remember from an earlier lesson is that we were able to split radicals apart. We're also able to combine them. So that's one of the things that we're going to do during this exercise here. I want to try and get everything that's alike together. So you can see that I've got these two coefficients here, the 2 and the 3. I want to get those together. So I'm going to go 2 times 3, and now I've got 2 square roots left. I'm just going to combine everything that's inside of those square roots into one thing. Because they are both square roots, they both got the same index, which means that they can be combined together. So I'm going to go the square root of 7 times 14 times t times t squared. Now I can work with everything that I've got here. So I've got 2 times 3 is 6, and then the square root of 7 times 14. So 7 times 14, 7 times 10 is 70, 7 times 4 is 28, so 70 plus 28 gives us 98. So we get 6 times the square root of 98, t cubed. Okay? So now what I've got to do is I'm going to see if I can simplify this radical at all. So I'm going to look at the factors of 98. So I've got 1 in 98, 2 in 49, and you know what? I'm going to stop right there, because I already know that 49 is a perfect square. I'm not going to continue on looking for more perfect squares when I already know that I've got the largest one possible. So I can break this 98 down into 2 times 49. So I'm going to go 6 square root of 49 times 2 t cubed. Now I've got 6, the square root of 49 is 7, and then what I want to do is I want to break this t cubed down. I'm going to go ahead and put the 2 in because I know that that 2 is not going to be coming out. The square root, again, has an index of 2. 2 goes into t cubed one time with 1 left over. So that means I pull 1t out and leave 1t in. So again, remember, your quotient is how many come out, your remainder is how many stay in. 6 times 7 is 42. T square root of 2t, and that's going to be your solution. So problem number 4 relates to something that if you've ever done it, you know just how difficult and how tedious it is. And that's moving furniture or moving anything through a doorway, because the doorway is a fixed size and you can only get certain things through it. So what we're looking at in problem number 4 is we're looking to see what size painting, what height painting can we get through a door. And in the case that we're given, the door is W units wide, and it's 3 times taller than it is wide. So we know that the height is going to be 3W. Now, the easiest way to get, or the greatest length that we've got going through a doorway is going to be the doorway's diagonal. So that diagonal is going to, we need to figure out what the length of that diagonal is in order to be able to figure out how big of a painting can we get through this doorway. Well, what you'll notice is that we've got a triangle that's created by that diagonal. And if this door was built correctly, then we know that that angle is going to be a 90-degree angle, which then tells us that we've got a right triangle. So if we've got a right triangle, we can then use the Pythagorean theorem. If you're not familiar with the Pythagorean theorem, it's a squared plus b squared equals c squared. What this means is that if we square each side, a and b, that's going to be equal to the square of the third side, or what we call the hypotenuse. So all we're going to do here is we're going to substitute in values for a and b in order to find what d is. So the values that we have are w, so we get w squared plus 3w, and make sure you put this in parentheses, so w squared plus 3w squared equals d squared. So w squared is w squared, 3w squared is 9w squared equals d squared. W squared plus 9w squared is 10w squared equals d squared. So now at this point we've got to figure out how do we get d alone. We're still looking to isolate d. So in order to do that, we're going to take the square root of d squared. Remember that whatever we do to one side of the equation, we also have to do to the other side of the equation. So if we took the square root on the d side, we also have to take the square root on this side. So that's going to leave us with, we know that the square root of w squared is w square root of 10 equals d. So the width or the height of the painting that we can get through this is going to be w times the square root of 10. So if we have a width of 5, then the height of the painting that we're going to be able to get through is 5 times the square root of 10. Okay, for 5a and 5b, we're going to do division. And in this case, you've got to remember one of the rules that we talked about with multiplication. You can take two radicals and you can combine them together into one, or you can take two radicals, or you can take one radical and you can split it into multiple radicals. So what we'll do with this is we're going to use that approach where we take one radical and we split it into multiple ones. Now, you don't have to do the splitting. You could just do the solving without doing the splitting, but I just want to make sure that you understand how this can be done. So we're going to take that square root of 64 over 49 and we're going to split it into two separate radicals. So square root of 64 over the square root of 49. So the square root of 64, that's a perfect square, we get 8, and then the square root of 49 is a perfect square, we get 7, so our solution is 8 over 7. In the second one that we've got here, we've got the square root of 8x cubed over 50x. Now, one of the things that we can do before we split them into two separate radicals is we can actually simplify inside this one radical first. So we can say, what goes into both 8 and 50? Well, we know that 2 goes into both 8 and 50. So in the numerator, we would divide out a 2 and we would get 4. And in the denominator, we would divide out a 2 and we get 25. In the numerator here, we've got x cubed over x. So we've got 3 x's in the numerator and we've got 1 x in the denominator, which means that we can do some canceling. That's going to leave us with an x squared in the numerator and no x's in the denominator. So we've done a lot of the work that we needed to do, and now we can go ahead and just simplify this. So if you want to, you can go ahead and split this into two separate radicals. You get the square root of 4x squared over the square root of 25. Square root of 4 is 2, square root of x squared is x, over the square root of 25 is 5. 2 and 5 cannot be reduced, and so you're done. In problem number 6, we're going to do something called rationalizing the denominator. Basically, one of the rules that you've got is that you're not allowed to have a radical in the denominator of your final answer. And so in order to avoid having that, you've got to do something called rationalizing the denominator. So in this case, we've got the square root of 3 over the square root of 7. Now normally you would look at that and you'd say 3 and 7, you can't do anything with that, so this would be the final answer. But it's not, because you've got the square root of 7 hanging out down in the denominator of this problem. So what we've got to do is rationalize it. In order to rationalize it, what we're going to need to do is to take this 7 and turn it into something that can be a perfect square. And so what that entails is just multiplying it by itself. So the square root of 7 times the square root of 7. But whatever we do to the denominator, we also have to do to the numerator. And so what this is now going to give us is the square root of 21 over the square root of 49, because 7 times 7 gives you the 49. Now the square root of 49 is just going to be 7, so we're left with the square root of 21 over 7. You may be tempted to take that 21 and that 7 and divide the 21 by 7, but you can't do that, because you've got to remember this is not 21, that's the square root of 21. The actual answer to the square root of 21 is somewhere in between 4 and 5. So you can't divide 21 by 7 in this case. So that takes care of that particular problem. Not too bad when you don't have any variables, but when you have variables it gets a little bit more complicated. Now with this one, we've got the square root of 7 over the square root of 8n. There's a couple of different ways to do this. I'm going to take you through the simpler process first. And if you like the simpler process better, just worry about using the simpler process. I'm going to take you also through a process that's going to keep your numbers much, much lower and not give you such gigantic numbers you're going to have to work with. It's a little bit more difficult to do it though, so you're going to have to figure out which method you prefer using. So in this case, I've got the square root of 7 over the square root of 8n. And what I'm going to do is I'm just going to multiply this by itself. So the square root of 8n. Whatever I multiply the denominator by, I've also got to multiply the numerator by. So I'm going to multiply it by the square root of 8n. 7 times 8 is 56, so I get the square root of 56n over 8n times, or square root of 8n times square root of 8n, which is the square root of 64n squared. Now, this is where the big numbers tend to hurt you a little bit, because now you got to do a lot of reducing. So basically what I've got to do is I've got to take this 56 and this 7, and now I've got to find what is the largest perfect square factor that I've got for 56. So I go 1 and 56, 2 and 28, 3 will not go into 56, 4 will go into 56 14 times, 5 will not go into it, 6 will not go into it, and then I get 7 and 8, which were the factors that I originally multiplied together. So the biggest perfect square factor is actually going to be this 4 and then the 14 that goes with it. So now I've got to take this and go square root of 4 times 14n over square root of 64 is 8, square root of n squared is n. Now square root of 4 is 2. I'm going to go ahead and erase my factors to give me enough room, times the square root of what's left over, 14n over 8n. Now I've got to check to see is there any reducing that I can do. The 2 and the 8 can be reduced, so this becomes the square root of 14n over 4n. Remember that the things that are in the radical and things that are not in the radical cannot be reduced. So this is going to be the simpler way of doing it, but you can see that it leads you to bigger numbers, which you then have to worry about later on in the problem. There is another method of doing this that's going to lead you to use smaller numbers, but you've got a lot more work to do at the beginning. So instead of multiplying by the square root of 8n, the first thing that I could do here is to actually break this down. So if I break this down, I can get 4 times 2n. And then that's going to take me to the square root of 7 over 2 times 2n. Now the only thing that I'm worried about in this denominator is what's in the radical. I don't care about this 2 that's sitting on the outside, because I know that that's already been taken care of. It's not part of the radical, therefore it's not a problem. So what I'm going to do is I'm going to multiply by the square root of 2n, and then multiply the numerator by the square root of 2n as well. And so what you can see is you get the square root of 14n in the numerator over 2 times the square root of 4n squared. Then what you'll see here, we can just leave the numerator as is, square root of 14n over 2 times, what's the square root of 4? The square root of 4 is 2. What's the square root of n squared? The square root of n squared is n. So now we get in the denominator 2 times n. Numerator stays the same, so 4n in the denominator. And you can see that it's a little bit more complicated up front. You have a couple more rules that you've got to remember, but you end up working with smaller numbers, which makes it easier on the end.